Hey everybody, in this video we are going to talk about the binomial distribution. And the binomial distribution is really a kind of a part of probability, so that's what we're going to be focusing on. And our big question of this video is what makes something a binomial distribution? Or maybe even put more specifically, what determines a binomial distribution? So what is it, and basically when can we use it? So there are four key factors that make something a binomial distribution. Let's just throw these out there. So the first one, there's a fixed number of trials. So if we're looking at some event, like let's say we're flipping a coin, we're flipping it 5 times. Only 5 times. It's a fixed number. We're not going to change that. Or we're rolling a die 7 times. We're rolling it 7 times. That's fixed. It's not going to change. So it's a fixed number of trials. The second thing is each trial has only 2 outcomes. And those 2 outcomes can be classified as success and failure. So if we were rolling that die, maybe we're trying to get a 6 on our die. So rolling a 6 would be considered success. Rolling a 1, 2, 3, 4, or 5 would all be considered failures. So we would lump the successes together and the failures together. So that way we've got only 2 outcomes that we're really considering. The third one, the probability of success, which we call P, the variable that we'll use is P, is constant from trial to trial. So this means that we're not going to use anything like drawing a card out of a deck and then drawing another one without replacing the first one, because that's going to change the probability as you go from trial to trial to trial. So the probability of success has to stay constant from trial to trial. And then the last thing, the trials are independent of each other. So that kind of also ties in with being consistent from trial to trial, right? So if we were doing a drawing of the card like I had just mentioned, and we took one out and we didn't replace it, we took another one out, now that second draw is dependent on the first draw. So the trials have to be independent of each other. Okay, so let's look at an example. The example is, we're going to find the probability of getting exactly 2 heads in 3 tosses of a biased coin, where the probability of getting a head is 2 out of 3. So for whatever reason, this coin is weighted, so you get heads more often than you do tails. So we're going to work on the probability of finding this, of getting exactly 2 heads. So we'll write this out, the probability of getting 2 heads. What's the best way to do this? Well, let's go back old school, the way that we used to find probability, and work on a tree diagram. So our first flip, we're going to get a heads or a tail, and the probability of getting a heads is 2/3. Probability of getting a tails is 1/3. Then we have our second flip. So if we got a heads the first time, we could get a heads or a tails the second time. Because these events are independent and the probability doesn't change, that's still 2/3 and 1/3. Or if on the first flip we got a tails, we would get the same thing. For heads and tails, we have 2/3 and 1/3. And then off of each of these, we know we're going to branch for another heads and tails with the same probabilities. It's going to go down the entire string here, where we're getting possibilities of heads or tails for each one of these. Okay, so now we're looking for exactly 2 heads. So let's follow our paths on our tree diagram. So we could go get a heads, and a tails, which would be 2/3 times 2/3 times 1/3, the probability to go just down that branch. Or we could have a heads, a tails, and a heads, which that probability is going to be 2/3 times 1/3 times 2/3. Or we could get a tails first and then 2 heads after that, and that would give us a 1/3 times 2/3 times 2/3. So you may notice that each one of these things is 2/3 squared times 1/3. So each one is exactly the same in this circumstance. And because we are we're looking at any of these 3 possibilities of happening, we have that or statement. We want either heads and tails, or heads, tails, heads, or tails, heads, heads, we would add all of these things together. So the probability of getting 2 heads is going to be 2/3 squared times 1/3 plus 2/3 squared times 1/3 plus 2/3 squared times 1/3, or 3 times 2/3 squared times 1/3. So if we want to calculate that out, we get 12 out of 27, simplify that down to 4 out of 9, and that's our result for this particular circumstance. So really, let's go back and check to make sure everything was good. So was there a fixed number of trials? Yes, there was a fixed number of trials, and that number of trials was 3. Was each trial considered a success or failure? Yep. Again, we had heads being successes and tails being failure. Was the probability of success constant from trial to trial? We do know that. That is also yes, that it equals 2/3 in every single trial. And are they independent of each other? Yes, again, that is the case. So we can say that is true. Now, typically you want to do this at the front end of a problem, so that way you make sure that you're going into it properly as opposed to doing it at the back, because then if you check at the end of the problem, you might say, oh, wait a minute, I did all this wrong, or I did all this for no reason, it doesn't fit the 4 qualifications. So, it's always good practice to do that first. Okay, so let's look at another example. Let's clear this off and look at another example. Excuse me. So, we're going to flip the same coin as before, where we get the probability of heads getting 2/3, being 2/3, but we're going to look at getting exactly 2 heads in 6 tosses. Now this is where the binomial distribution starts to come in handy, when we start getting more and more trials. Because if we had just 1 or 2 or 3 trials, we can do a tree diagram, it's no problem at all. If we start getting 6 trials, 10 trials, 20 trials, 30 trials, then it starts getting a little bit more complicated with those tree diagrams, most definitely. And we want to look for some kind of shortcut. So we're going to do a shortcut here. But as I mentioned before, let's make sure that we've got all the right information. We kind of know this already, but let's do it just to be safe. Are there a fixed number of trials? Yes. There are, our number of trials is 6 for this case. Does each trial have only 2 outcomes, a success or a failure? Yes, again, we know that we're going to consider heads our success, tails our failure. So we've got our 2. Is the probability of success constant? Yes, it is. It is always going to be 2/3 for this particular coin. And are the trials independent of each other? Yes, again, they do not impact each other. Okay, so now we can proceed. I know it seemed a little redundant, but like I said, it's good to get used to checking this before you jump into the binomial distribution. Okay, so we know that our previous problem, that a success was 2/3, a failure was 1/3. And in the previous problem, we saw that when we were going through all the different branches, we were looking for 2 heads. And what we found was that every single time 2 heads, we had 2/3 times 2/3. So we know that this is going to be looking for 2 heads, so we're going to get 2/3 squared again. Then in the previous problem, we had the leftover results being a probability of 1/3. In this case, because we're looking at 6 tosses, the leftover is going to be 4, so we're going to take 1/3 to the 4th power. Now the only thing that remains is what's happening in front of here. Before we multiplied this by 3, so it'd be nice to say, oh, we just multiply this by 2 or we multiply it by 6, but it's actually not that easy. This value came from Pascal's triangle. So we did this in previous videos. We worked on Pascal's triangle, but this thing comes from this coefficient comes from Pascal's triangle. So we either used NCR, a combination, or we used the notation N of R. So in this case, N is the number of trials that we're doing, and if you remember, R is how many we're looking for, how many we want. So we want 2 heads, right? So that's what we're looking for. So that's our R. So if we were to punch this into our calculator, we would get 6/2. And if we kind of looked at Pascal's triangle, or I should say, yeah, if we're looking at Pascal's triangle, we're looking at the 6th row and we're looking in the 3rd position. And why do I say the 3rd position? Because remember that when we're finding r, that 2 value, that starts at 0, then it goes to 1, 2, and so on all the way up to n. A lot of people forget that 0, so we can't forget that. Now, if we were to calculate all of that 6th row of Pascal's triangle, we would get the values 1, 6, 15, 20, 15, 6, and 1. So we're looking for the third position because 2 comes in the third term in that sequence. So we're looking at 15. So this ultimately ends up being 15 times 2/3 squared times 1/3 to the 4th power. As we start multiplying that out, 15 times 4 over 729, or 20 over 243. And if you wanted to simplify that or convert that to a decimal, we could say it's approximately 0.0823. So on this biased coin, getting exactly 2 heads, no more, no less, in 6 tosses is approximately 8% of the time we'll get that. So that's how this works. So let's kind of look at the summary. X is a binomial distribution when we can say, or X is binomial distributed when we say X, kind of that squiggle, B, N of P, or NP. So this is basically the notation that we use to say that we're talking about a binomial distribution. So if you see this notation, X squiggle B N of P, that should indicate to you, okay, I need to do a binomial distribution. X is going to be my random variable, B indicating that I'm doing a binomial distribution, N is the number of trials that we have, P is the probability that we have, and we can kind of work it out from there. Okay, so from that, as I mentioned, N is the number of trials, P is the probability, and we can say then that the probability of X equals little r, which is what we're looking for, how many we want, and that's going to be n of r, or the combination nr, times p to the r. So if we look back at our example here, we had 2/3 squared, and when we're looking at the r of our NCR, 2 was that r value. So we're taking the probability of success to the r power times 1 minus the probability of success, which is going to be our probability of failure. So that's always going to be the converse of that. And we're going to take that to the n minus r power. Right? Because here, before we had 6 trials, we wanted 2 heads, so that left 4 left over, so that's what we took our failure to be, n minus whatever our r is. Okay, so that is our basic formula for the binomial distribution. That's the one you should know and get familiar and used to, and that's keep in mind that we are using our NCR in there, so that's going to be new. The rest of this should be fairly straightforward. We're using the probability of our success and whatever our R is, however many we want, right? So that is binomial distributions of probability. I hope that helps kind of either review or get you set up for working with this type of thing. And I will talk to you in the next video. See you later.